Today I shall be talking of shape fabrication using pressing. In many earlier classes, I had referred to die pressing, where we take the powder and pour it into a die and press. I talked of the differences between uniaxial and biaxial pressing, where I had stated that the uniaxial pressing, because the pressure is principally from the top, there's a large distribution of pressures, and as a result, the compaction of the die is not uniform. Whereas in biaxial, pressure is applied from the top and the bottom, and hence the compaction by biaxial pressing is a little bit better than uniaxial pressing. Normally, in a green body, that is, the pressed pellet before firing, we expect an open porosity or the porosity of about 60% to 50%. We do not expect a packing density which is more than 40% or 50%, simply because of the differences in the pressure. The particles do not get packed very well. Now, I had also talked of earlier that during sintering, if porosity is high in green bar shape, then after sintering, this body will remain porous. If it's say 50% porosity is there, I may drive this 50% down to 80% to 20% porosity, or 80% dense. Yet we are very far away from the theoretical 100% density. This is simply, as I said, due to particle packing problems, the lack of uniform pressure during pressing, and as a result, differences in sintering rates at various places, and the porosity remains about 20% or so in spite of the best efforts. So what do we do to get a very dense ceramic product? An example of a 100% dense ceramic is, for example, the spark plug. Whoever drives a two-wheeler or a four-wheeler or a three-wheeler has an engine, and spark plug is an essential component of internal combustion engine. that material is 100% porous. So how can we achieve almost 100% theoretical density? I said the spark plug is 100% dense. I made a misstatement. So the question is, how can we obtain 100% of the theoretical density or close to it in sintered products? I had referred to some materials as sintering aids earlier. That is, materials which cause formation of glassy media. The glassy media dissolves the particles, causes reprecipitation. A good example is, for example, the higher end porcelain teacups. Now they are 100% dense, no doubt about it, but they have a glassy phase. Whenever a ceramic and a glassy phase are there, there is a thermal expansion mismatch, and hence that material may not be able to withstand high thermal or mechanical stresses. For example, the spark plug in the two-wheeler, three-wheeler, four-wheeler, whatever you're using, it is subjected to a 10 kV discharge about 1,500 times a minute. So the thermal spark plug, the spark plug in the automobiles have to withstand not only high thermal stresses but high mechanical shock. If there is a ceramic and a glassy phase, the thermal expansion would have been different. Fracture would have occurred along the grain boundaries. The glass could have melted. Lots of problems. So the spark plug has 100% density, uniform grain size, because let's say we have got this small grains in the sintered body and suddenly we have a large grain in the sintered body. So obviously here the mechanical property would vary from place to place depending on where we are. So we require uniform grain size and 100% density. One way of doing it is hot pressing. I am taking up hot pressing because where I'll end up with, this is the first step or the first method people had used. A hot pressing is no different than biaxial pressing, except for one fact. Here is a die the anvil, the hammer, and here is the powder. This is biaxial pressing. So how is hot pressing different? In hot pressing, the whole thing is kept in an evacuable high temperature vessel. Here in this hot pressing, what we will have are heaters all around it. Heaters all around it. As a first step, one, evacuation of chamber. Second, heating the die to desired temperature. That is, when I heat it, it's not only the die, but the hammer, the anvil, the powders all get heated. So it is, the whole system gets heated. 3, press. 4 is just reverse. After the desired pressing, we remove the pressure, we remove the decrease the temperature to room temperature. We remove the pressure and take this material out. Take the pressed material out. Now, what is that? How is it that hot pressing is more advantageous than cold biaxial pressing? In these cases, the material is heated to at least 1000, 1200 degrees centigrade, if not more, depending on the material. At these temperatures, the grains plastically deform. That's the first thing. So they plastically deform, pack better. Secondly, at these elevated temperatures, the diffusion rates increase, and hence sintering accelerates. Third, due to the higher elevated temperature, the inclusions, the pores, the defects, they all migrate to the grain boundary and the surface. So as a result, in a hot pressing, we have one advantage due to high pressure and temperature. Sintering is faster, and so sintering can be done at temperature lower than normal sintering temperature. And lower than normal sintering temperature. However, in spite of these advantages of hot pressing, we have severe issues in using a hot press. Firstly, whatever die material you use, it will have a thermal expansion. So during heating, the die will expand. The hammer, the anvil also will expand, and when you cool, they will contract. The problem is that what happens to the pellet out here? If the pellet has a smaller thermal expansion coefficient than the die, what would happen? It would expand less and just retain the size it has after sintering. At times, the thermal expansion mismatch is so bad that the pellet simply gets stuck inside the die. So, one problem is the thermal mismatch problem of the die, the anvil, the hammer and the pellet are a matter of serious concern. And unless one can really address this problem, hot pressing will be very difficult. However, people have done, they have got sintered alumina disc by using alumina die simply by using alumina die, hammer and anvil have Tg less than 80 and yes, those two. So, if I am pressing alumina, it is better to use an aluminum oxide die as a complete set, because there the thermal expansion mismatch question does not occur. But in most of the metals, we will have die wall powder reaction which has to be cleaned out. Secondly, what we will have is this differential thermal expansion of the pellet and the die wall. If somebody uses silicon carbide for hot pressing, then the die will change to immediately silicon carbide. The die will have to be made of silicon carbide so that the die will have to be made of silicon carbide so that the thermal expansion mismatch does not occur. This renders this process very expensive because the gases have to be pumped out, fresh gases have to be put in. The die wall, its longevity, as I said, is up in question, and hence hot pressing really has not found good takers. Of course, they have been overcome by other events in ceramic industry and which are far more easier to handle. One of the easiest methods to handle pressing to almost 95-96% of the density in the green stage and 100% density in the dark age. One way is to do what we call isostatic pressing. Isostatic pressing, I will come to the diagrams and the details. Here, as opposed to biaxial pressing, what happens is Well, there are variations to this. Let me say, I drew one variation. All of this outside, which you see, this is a rubber mold. Here we have got here's a powder, and we want to get a powder shape which is exactly the same size and height. So what is done? This is a rubber mold with channels to either press gas or it can be liquid. Inside it, I've got a rubber mold into which a mandrel is placed. The gap is filled with powders. Now, this whole assembly is placed inside it, and the tops again sealed the same way so that it remains gas tight. Then you apply gas pressure, apply gas pressure, and after the gas pressure, say it can be up to 1500 megapascal. After you apply the gas pressure, have given the residence time, you take away the mold. What will happen? This rubber mold under pressure would have squeezed much more, which manually is not possible. Further, this pressure acts in all directions. So this is better than uniaxial pressing, where uniaxial pressing we had pressure only from two directions, but here we have got pressure from three different directions. And hence, after the pressure is allowed to drop, this particular what would happen is these powders would get compacted very uniformly, and I would get almost 99% compaction. I would ask you to look at this particular video where here the sample is put into the die cavity. Here is the top plug coming in so that the air is squeezed out, any free air, and then the top part is screwed shut. At that point, processing means the pressure increases, the pressure is kept on increasing, and then the pressure is held, and after that the pressure is released. the top die part is taken off. Yep. And these shapes with 100% density are easily fabricated by this wet bag, dry bag process of cold isostatic pressing. So, this one was what we call, because gas was used, so we call it dry bag pressing. If we use a liquid, it will be wet bag isostatic pressing. Now, the advantage of this isostatic pressing is we get almost 100% theoretical density, 100% theoretical density in after firing, and before firing the porosity is hardly 0.5% or so, and there is no lack of uniformity in the structure right across the sintered body. Well, with cold isostatic pressing, one does have to sinter the body to get a sintered product. However, if we increase the temperature of this processing in your mother's unit, other one is basically hot isostatic pressing. There are plenty of YouTube slides. Let me go with this one. This was one of the first hot isostatic presses developed at by Memorial Laboratory, and that one was the very first one. And with that, we can make complex shapes not only of crucibles or so. Here, what happens is, as you can see, this is chamber, this is the work chamber, the heat is. The heat is, and this is inside a completely this size is a complete box. The sample is placed over here, the heaters are outside, and the thermal insulations are over here. And inert gas is passed in. When this is done, the higher temperature, which was the advantage of hot pressing, helps in making the diffusion process easier, and as a result, here we get hot isostatically pressed materials. I will let this slide carry on to show you what are the complex shapes which have been generated. As I said, densification of powdered materials to 100% of theoretical density, that's important. And at the same time, the internal porosity is also avoided. This is how the interior of the hot pressure vessel looks like. This is how the inside chamber. I can have different types of shapes placed inside the inside chamber. Look at the vessel rising. Okay. These are the various gas manifolds through which the gases flow into the chamber. Here the chamber is closing by itself automatically, and the whole thing is being pressed, put in a closed container where the temperature is changed, ramped up after applying the pressure. Temperature is held for a predestined time depending on the material. You can start off with the powders. You can have multiple different shapes. Look, the advantage of hot pressing is there is hardly any isolated or internal porosity. We can have multiple materials made using the hot press at the same time, and as I said, this open porosities are removed. Your finished final sample. This is another video on hot isostatic process. look how hot isostatic pressing helps in making the grain boundary merge together. Well, using these three methods, hot pressing, cold isostatic pressing and hot pressing, we get very, very dense products. However, let me assure you, as usual, there are limitations to every method, and hot press and these methods, which are very, very expensive and capital intensive, will try to give powders or compacts of as much desired density is required. The costs are very high. Furthermore, one more question remains is, when we say hot press silicon nitride, at elevated temperature silicon nitride breaks up. So, what is done is, if these are hot press silicon nitride rotors, I would have silicon dioxide coating all over the surface. Why? In that case, if this is a silicon nitride surface, then from the surface oxidation occurs. Silicon nitride breaks up. So, what we do is, on the silicon nitride shape we coat SiO2 powder, which acts as a cap and prevents the breaking up of silicon nitride. There are various problems, expense with reference to hot pressing, hot pressing, hot isostatic pressing, cold isostatic pressing, and one has to deal with particle size, shape also, even though I did show you that with hot pressing or hot isostatic pressing, the plasticity increases and the grains merge far better. Now, one thing I hope you noted, that in hot pressing, cold isostatic pressing, hot isostatic pressing, there are quite a few materials I had not used, which I used in uniaxial pressing. I did not use any binder. I did not use any lubricant, which helps in the sense that contamination is not that high. However, with hot pressing, as I said, die wall reaction is definitely a major problem, and one has to handle the die wall reaction by choosing dies which are similar to the material which you are pressing. So, the idea is, if you are pressing alumina, use an alumina die. If you are pressing zirconia, press a zirconia die, use a zirconia die. If you are using carbides, use a carbon die and die punch, sorry, so that the thermal expansion coefficients pose less problem, die wall powder reaction is minimized, and hence all these factors limit our options in hot pressing. Further, another problem is, in hot pressing, only certain specific shapes can be done. Today, another technique which is called pseudo hot pressing, this is used. This is used for complex shapes. what would I use as a complex shape? Let's say this particular pen. I want to sinter the powder to this particular shape and length. It means that biaxial pressing or uniaxial pressing is out because the dimensions vary. What would I be doing? I would be knowing the volume thermal expansion of this and this part, so that we have calculated for the expansion, have seen the pressure is not that high, there is due to the volume thermal expansion, and that becomes 1. So what I would do is I would take a chamber, a die, fill it with the granules of the alumina, zirconia, or whatever you are using. And let's say over inside we have placed this particular shape. This is all filled with inert materials. This is fundamentally a pseudo hot pressing, and in this way some shapes are indeed generated. So we have covered uniaxial, biaxial, hot pressing, cold isostatic pressing, which is also referred to as SIP, hot isostatic pressing. These are all the fundamental pressing techniques that, for example, look at this particular one.
Isostatic pressing basically is the application simultaneously of heat and pressure to any given component. It could be a casting, it could be powder, it could be used in a diffusion bond. There's just a myriad of places that it can be used. They use it for cosmetics, medical, MIM, powders. And that could apply again to any area of manufacture. Aerospace is a big user of it right now, but commercially it's used in oil and gas. It's used in the medical area for new knees, new hips quite often. You can do things from as small as a tiny little dental bracket or as large as 10 to 10-ton, 14-ton pieces. All you need is the right size unit to do it. It's very simple and straightforward, but it has its benefits. As to the future of HIP, I think that powder is going to be probably the foremost leader in HIP, and I think that also areas like MIM, metal injection molded parts, where high stresses are being used or they need high wear resistance for the material, will also be large markets for our group. I believe also that sputtering targets for the electronic industry, those may be in the form of billet, or those may be in the form of diffusion bonded pieces.
What are the possibilities with hot isostatic pressing? The opens are limitless. You can virtually design any shape as you want. In the next one, what I shall be doing is, now that the pressing techniques are over, I shall be dealing with other shape forming processes. Like I had started off with doctor blade process. I will be dealing with it a little more, the problems, how to avoid them. I talked of earlier of making slip casting. I had shown you certain diagrams. I'll be working on them also. And then we will be looking over at other processes. One process which I would take up even before I take up slip casting is, or doctor blade process, is chemical vapor infiltration process. You see, many of the real world ceramic materials are composites. That is, they have got two items. Let's take say silicon carbide fibers in alumina matrix. Alumina has got its own hardness, but if we can put in silicon carbide fibers inside the alumina, the strength would be increased. Like say this is the alumina matrix and we have got silicon carbide fibers right through it, right across. The strength would be phenomenal. Can we also do alumina fiber in silicon carbide matrix? In the next class, we will look at the possibilities of shape fabrication using what is called the CVI or chemical vapor infiltration process. And thereafter, I shall go over to doctor blade process. Now, about the CVI process, the Japanese developed a single process and they called it Langside. I'll dwell with it when I take it up. Within 7 days, they had 1,000 patents guarding this process. Now, in ceramic shape fabrication, this is one of the most important things. Broad areas are known. Uniaxial, biaxial, hot isostatic, cold isostatic, hot press. But when you really want to go to make a sample, there are tiny variables. That is powder size, powder shape, dye filling, what is the rate of temperature you are going up, residence time at that temperature, there is a time you hold the sample at that temperature, cool down rate, all of these are proprietary information, not available anywhere. It is only the company who has done it really knows. And so, honestly, when I am discussing these things, I can only give you only a very broad overview. As I said, even though I am aware of exactly how this is done in a particular case, I cannot bring it up here due to intellectual property rights. Yet, when I talk of this chemical vapor infiltration Lang-side processes, I will try to be as clear as possible, try to give you some hard ideas. Thank you.